the Big Bang, that beginning of our universe as we know it. But how do we know about this incredible event that happened billions of years ago? After all, we were not there. Well, that is a story of incredible surprises, amazing people, and a little bit of physics. 100 billion galaxies out there, each of them with 100 billion stars. All of that is only 5% of our universe. Every galaxy was moving away from us. And the further the galaxy was, the faster it was moving. That is a clear signature of expansion, which therefore implies a trigger that started the expansion. Chances are you have used a quantum device today. Your phone, maybe, computer, laptop, camera, TVs, projectors, telescopes, medical devices. All of these are possible because we know how to control matter and light at the microscopic level. And the reason we can do this is because of the theory of quantum mechanics. But this theory is so much more than a tool for building technology. It actually allows us to probe the deepest mysteries of the universe, including the Big Bang, that beginning of our universe as we know it. But how do we know about this incredible event that happened billions of years ago? After all, we were not there. Well, that is a story of incredible surprises, amazing people, and a little bit of physics. And it begins in the stars. So this is a very high-resolution photo from NASA of our sun. But about 150 years ago, the sun and other stars looked more like this to astronomers. Each bar here is actually light collected from a star and separated out into its spectrum of colors. And you may notice something here. There's lines in the spectrum, dark points. And these are missing colors. They are missing light. And explaining why this light is missing was one of the early successes of quantum physics. The light is missing because it's actually been absorbed by gas around the star before it came to Earth. And quantum physics allows us to figure out exactly which gas will absorb which color. So by looking at those missing colors and that set of lines, we can figure out what that star is made up of. Almost all the information in the universe comes to us encoded in these kinds of images, the barcodes of the universe. So in the late 1800s, at Harvard Observatory, they were performing studies of stellar spectra of this kind. And the head of that observatory was a man named Pickering. And he wasn't too happy with the progress being made on this work by his team. So he decided he's going to hire his housekeeper to do this job, a woman named Williamina Fleming. Well, she started and she was good. She was really good. In fact, she started finding patterns and built a star catalog, the first of its kind. Pickering was very happy, of course, especially because she was much cheaper than his male employees. So he decided that he's going to hire more women at a discount price. And the women happily signed up because there weren't that many chances to do astronomy back then for women. These women came to be known as the Harvard computers. And together, they explored and classified hundreds of thousands of stars, building a catalog that is the basis of our knowledge of the universe today. Many of them became famous astronomers in their own right, and one of them played an incredibly important role in the story of the Big Bang. Henrietta Leavitt was looking at stars that are called Cepheid variables, and what those are stars that actually change in brightness over time. They become brighter and dimmer periodically. And what she found out was that the rate at which they become brighter and dimmer depends on how much total energy they are emitting. So the more energy the star is emitting, the faster it'll oscillate. So just by looking at the oscillations, we can figure out how much energy that star is emitting. And that's important Because then, if we know the actual energy of the star, we can look at how bright it looks to us on Earth and figure out how far away it is. The brighter it looks, the closer it is. And the dimmer it looks, the further it is. For the first time, we had a way to measure distances to other galaxies, stars in other galaxies. And that opened the door to the universe. In 1929, Edwin Hubble used Leavitt's method to measure distances to various galaxies. And he also used these spectra of galaxies to look at how the galaxies were moving. And he found something incredible. Every galaxy was moving away from us. And the further the galaxy was, the faster it was moving. That is a clear signature of expansion, which therefore implies a trigger that started the expansion, the first evidence of the Big Bang. NASA, as you know, has named its flagship telescope the Hubble telescope after this amazing astronomer's discovery. Henrietta Leavitt, not so well known. In fact, Hubble himself did acknowledge Leavitt's work, and she was nominated for a Nobel Prize, but by then she had unfortunately passed on. So Hubble's work and his amazing discovery certainly told us that there was a Big Bang event, but it was indirect evidence. Direct evidence came much later and totally by accident. So in 1964, a couple of astronomers at Bell Labs were studying radio waves using a huge telescope, a horn antenna. And what they kept getting was this noise, a background noise that they couldn't get rid of. Well, there were pigeons living in the telescope, so they figured that's what it was. But the real reason was much more interesting. That noise, that background noise, is everywhere around us. It's the leftover energy of the Big Bang. Today, we have been able to use our best telescopes to map this radiation that is all around us, in this room, in the sky, everywhere. That's the cosmic microwave background radiation. It's ancient light. It comes to us from almost 14 billion years ago. How do we know 14 billion years? Well, when Hubble was measuring that expansion of the universe, he measured the rate at which that happened. So then, he was able to rewind at the right speed and wait to see how long would it take to rewind right to the beginning. And that's how we got our estimate of the age of the universe. Again, today, after Hubble's initial calculations, this has been done using our best telescopes over and over again, measuring the rate of the universe, including the Hubble telescope itself. And today we can celebrate the 13.8 billionth birthday of the universe. But our telescopes tell us so much more. Recent measurements of this expansion gave us another big surprise. In fact, the universe is expanding faster and faster. Something is pushing outwards. We don't know what it is. We call it dark energy. But even though we don't know what it is, we can use our knowledge of the background cosmic radiation, which comes from the Big Bang, and try to figure out how much of this dark energy there is. And here's what's amazing. 100 billion galaxies out there, each of them with 100 billion stars. All of that is only 5% of our universe. The rest is dark matter and dark energy. We don't know what it is. But that's good. It means we have lots to learn. As our telescopes get better and we get more data, we're going to find out new and amazing things. In my own research, we look at how does the microscopic world connect to these macroscopic scales. What does quantum physics tell us about the nature of reality? Is there even a reality out there? Why do atoms move in a different way than celestial bodies? How can we explain that? Are there multiple universes out there? I'm here to tell you that it's a good time to be a physicist. But I'm also here to tell you that as a woman physicist, we must acknowledge and celebrate all the contributions that have been made so far in this story, both by the men and the many forgotten women in this story. Because we need to inspire future generations of men and women to follow in the footsteps of Hubble and Leavitt. And finally, I'm here to invite you to experience today the Big Bang for yourself. If you have an old TV or a radio and you're looking for a channel, the most interesting channels you can find are actually the ones without programming, the ones with the noise, the static, because a little bit of that static, that noise, is the same noise that Wilson and Penzias found so long ago. It's the leftover sparks of the Big Bang. So let's take a moment to listen and to observe our own origins. All around us, literally, nature has left us clues. The universe is just waiting to be discovered. Thank you.